Okay, so we chose problem 3 from the SCUDEM 2024 problem set. My name is Emma Jackman.
I'm Marshall Tentis.
I'm Alex Lobo.
And we are doing standing against a mammoth. So for some background information, Clovis points are a lot of things, but most importantly, they bulge out on the sides, they have a rounded bottom and a pointed tip. And then the top picture is a picture of the Schoningen spear. These were spears found during the Paleolithic time period, and a lot of our research will be based on them, and we will mention them again in the end. So, this is set in the late Pleistocene in Clovis, New Mexico. The mammoths we will be talking about are the Columbian mammoths. They were some of the biggest mammoths. They had really long tusks, and fortunately for us, they were herbivores. The hominids at the time were Homo sapiens. Although there were Neanderthals, they were not on the North American continent yet.
Yes, our main plan of attack, we are finding the equation for efficiency, and that's dependent on the mass, the tensile strength for the barrier, and that's just the skin of the mammoth, the area of impact, and the acceleration of the spear. We are finding the equation for the cross-sectional area of the Clovis point in the XY and the XZ plane, and those will be elaborated on later, and we'll also need to find the equation for the mass of the spear. For the data and information, for experimental purposes, many heights and widths have been used in calculations to provide ideas into the optimal Clovis shape, and in our functions we're including h and w, and those are just height and width, and they're constant variables.
Okay, efficiency equation. So we know the efficiency is the same as the useful output over the total input. Useful output is the force needed to break the skin of the mammoth, and total input is the force applied to the spear. This equation is versatile as the total input can be changed according to how the spear is used. Either there will be an acceleration derived from a two-dimensional trajectory of a throw, or it will be from one-dimensional movement of the mammoth.
So our first equation is going to be the xy cross-section. So we used a parabolic function and a sinusoidal function. The first one, y1, is a parabola that modeled the face on view of the Clovis point, and the second is a sinusoidal function that modeled the fluted bottom of the Clovis point, or y2. Fluting generally reaches a height of 1/3 of the Clovis, and some assumptions we made are we assumed a parabolic shape to be the outside edge of the Clovis. We assumed a sinusoidal shape to be the bottom edge of the Clovis. We assumed fluting will always reach a height of h/3 based on our research, and we found the area of the cross-section through integrating the area between the curves with bounds relative to the Clovis's width.
Okay, so to find the equation for the cross-section, we have the y1 and the y2, and those are respectively the parabola and the sinusoidal curve, and those were derived just through using the normal characteristics and kind of like using trial and error to kind of tailor it exactly how we wanted it to. So we have the integral subtracting the two, and that will give us the area of the cross-section in the xy plane.
Alright, so now we're going to look at some graphs. So the first graph we're going to look at is Clovis points that have a width of 3 centimeters. The first graph is one with a height of 6 centimeters, the second has a height of 9, and the third has a height of 12, and you will see these heights often in the rest of our graphs during our presentation. And you can see the areas above. With a width of 4 centimeters, these are the graphs with the same heights respectively. And a width of 5 centimeters, once again, these are the same heights respectively. And the areas you saw got a lot bigger. So for the XZ cross-section, some background, we used two parabolic functions. The first one is the same parabola that modeled the face on view of the Clovis point in the XY direction. And the second is a parabola that modeled the side view of the Clovis point in the YZ direction. It's important to note that Clovis points we found are generally widest at half of their height. So some assumptions. We assumed a rectangular shape to simplify area calculation, although it's important to note this is not accurate. h/2 we assumed is the widest point of the Clovis point, and therefore will always represent the entire impact area. We found our x and z components by setting the plane h/2 equal to each parabola and solving. And we also assumed during each impact the area of impact is the max area of impact, and that this will always be parallel to the impact surface.
Okay, so we have the y1, this is the previous parabola used, y2, this is the parabola for kind of the side view of the Clovis point, and y3, that is the plane at h/2, which is just half the height of the parabola, and they'll cut through the two equations and give us the cross-sectional area. So we just set those two equal to each other, and then we find the x and the z values from doing that, and we multiply those together to find the cross-sectional area in the XZ plane.
Okay, so similar graphs, the same widths and the same heights as last time, although this time we're in the 3D, so it looks a little bit different. We're also looking top down. And like we said before, this is the XZ plane. So down here at the bottom, we only have one picture, and that is because the cross section, if you noticed in our math before, if you're paying really close attention, the H actually cancels out. So the cross section is not dependent on H. So these all actually have the same cross section, and our values are to the left. For width of 4, same thing, H's still cancel. And for width of 5, once again, the H's cancel and they all have the same cross section. So our final step towards our final equation is mass. So we use the XY cross-sectional area and WZ to find a volume. WZ was an equation from the last thing we just talked about. Flint was one of the most common materials for the Clovis point, and the Schoeningen sphere number 2 is one of the best examples of what a spear handle would look like for this case. The accepted wood type for that approximation is Picea abies, and some assumptions. It's important to note volume is an extremely rough approximation. The density of flint is 2.622 grams per centimeter cubed, and the density of Picea abies is 0.509 grams per centimeter cubed. The radius of the Schoeningen sphere number 2 is approximately 1.7 centimeters, and the length is 230 centimeters.
Good. So the equation for the mass. So the mass of the total sphere is going to be equal to the mass of the Clovis point added to the mass of the shaft. And so for the mass of the Clovis point, we just have the cross-sectional area times the width in the z direction times the density of flint, which is the constituent material of the Clovis point. And then for the mass of the shaft, we have the density of wood times the volume of the cylinder. And we, again, just kind of what I was reiterating, and we just kind of plug in all our values and note that that isn't grams, as we do have a mass.
Okay, the background on efficiency equation. We use sigma to represent the tensile strength, so this is how tough the skin is. We use A to represent the area of the impact, in this case the XZ cross-section. We use A, we know that's the acceleration, which is the second derivative of position with respect to time. And we use M to represent the mass of the sphere. The assumptions for the efficiency, we say sigma of stratum corneum was used. We say that A was approximated by a rectangular shape created by a plane intersection, and we say the mass was found using an approximation volume and densities. The equation for efficiency. So we know that F break over F applied, that's our efficiency. F break is going to be sigma times the area of impact, and well, F applied will be MA, and well, we replace the acceleration with the derivative with respect to time of position, the second derivative, and then we use sigma to be 2 joules per centimeter cubed, and we substitute all known values and we get our final equations for efficiency. Additionally, note that the efficiency doesn't have units, and it's just a ratio. Safety concerns. Although it is true that bracing a spear would reduce the applied force, it is negligible when taking into account how dangerous that would be. The average length of these spears was about 230 centimeters, about 7.5 feet. Although that is quite long, it is important to recall that their tusks often reach 400 centimeters, 13 feet or more. We argue that the safety risks of this are much too high to be common practice for early hominids.
Those are sources.
Yeah,
Thanks
thank
for
you.
watching.
Cheers.